Placing the disconnect, sometimes referred to as a disco, ahead of the meter base is a design choice that may seem counterintuitive. However, there are several reasons why an engineer might specify this configuration, especially in a commercial setting. The most prevalent reasons are protection for the meter, isolation for maintenance, and security. Firstly, protection for the meter is a primary concern. The meter is a crucial and often sensitive component in the electrical system, and it's essential to protect it from potential damage. Placing the disconnect upstream of the meter provides a safeguard against short circuits or overload occurring downstream. If a fault happens in the downstream panel or connected equipment, the disconnect can quickly shut off power, preventing the surge from reaching and potentially damaging the meter. This is particularly important in commercial environments, where electrical loads can be substantial and unpredictable. Secondly, isolation for maintenance is another significant advantage. The disconnect acts as a readily accessible point to energize the entire electrical system downstream, including the meter and the indoor panel. This isolation is crucial for performing maintenance repairs or upgrades safely. Without a disconnect, maintenance personnel would have to rely on the utility's disconnect, which may be less accessible or require coordination with the utility company. Having the disconnect readily available ensures that the electrical system can be safely isolated, preventing accidental energization during work. This protects workers from electrical shock hazards and allows for efficient and safe maintenance procedures. Thirdly, security is an often overlooked benefit. The disconnect provides a physical barrier to unauthorized access to the electrical system. It can be locked or sealed to prevent tampering with the meter or unauthorized use of electricity. This is particularly important in areas where there is a risk of theft, vandalism, or illegal connections. The disconnect makes it more difficult for unauthorized individuals to bypass the meter or draw power without being detected. In addition to these primary reasons, local codes and utility regulations may also play a role in determining the placement of the disconnect. Some jurisdictions may require the disconnect to be installed ahead of the meter base as a standard practice. This requirement may be based on specific safety concerns or to ensure compliance with utility policies. It's always essential to consult with local authorities and the utility company to verify any applicable regulations before making changes to an electrical system. They can provide specific guidance on the required configuration and ensure that the installation meets all applicable standards. When considering changes to an electrical system, it's also important to evaluate the existing infrastructure and the specific needs of the building or facility. Factors such as the size of the electrical load, the type of equipment being used, and the potential for future expansion should all be taken into account. A qualified electrical engineer can assess these factors and recommend the most appropriate configuration for the electrical system. In summary, while it may seem simpler to have the meter base ahead of the disconnect, there are valid reasons why an engineer might specify the opposite configuration. Protection for the meter, isolation for maintenance, and security are all important considerations that can justify placing the disconnect upstream of the meter. Additionally, local codes and utility regulations may also influence this decision. Understanding these factors can help ensure that the electrical system is installed safely, efficiently, and in compliance with all applicable standards. An electrical system operating at 208 volts 3-phase 200 amps represents a significant electrical service commonly found in commercial and industrial settings. To fully understand the implications of the disconnect and meter placement, let's delve deeper into the components and considerations involved. The 208-volt 3-phase system is a standard voltage configuration for many commercial buildings. The 3-phase power provides a more efficient and balanced distribution of electricity compared to single-phase systems. The 200 amps rating indicates the maximum current that the system is designed to handle. This dictates the size of the conductors, overcurrent protection devices, and other components within the system. The disconnect, as previously mentioned, serves as a crucial safety device. It's essentially a large switch that can completely cut off power to the downstream circuits. Disconnects are typically rated for the maximum voltage and current of the system. They must be capable of interrupting the full load current and withstand the fault current that may occur during a short circuit. There are different types of disconnects available, including fused disconnects and non-fused disconnects. Fused disconnects incorporate fuses that provide overcurrent protection in addition to the disconnecting function. Non-fused disconnects rely on separate circuit breakers or fuses in the downstream panel for overcurrent protection. The meter base is the enclosure that houses the electrical meter. The meter is a precision instrument that measures the amount of electricity consumed by the building or facility. The utility company uses these measurements to bill the customer for their electricity usage. Meter bases must be installed according to utility company specifications and local codes. They typically include provisions for sealing the meter to prevent tampering or unauthorized access. The indoor panel, also known as a distribution panel, is where the electrical circuits for the building are distributed. It contains circuit breakers that protect each individual circuit from overloads and short circuits. The panel is fed from the meter base and provides power to lighting, receptacles, equipment, and other electrical loads throughout the building. The conductors that connect these components must be sized appropriately to carry the full load current. The National Electrical Code, or NEC, provides guidelines for conductor sizing based on ampacity and other factors. It's crucial to use the correct wire gauge to prevent overheating and potential fire hazards. Grounding is another essential aspect of the electrical system. Grounding provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to trip and clear the fault. Proper grounding helps to protect people and equipment from electrical shock hazards. The NEC specifies grounding requirements for different types of electrical systems. These requirements must be followed carefully to ensure safe and reliable electrical installation. When designing or modifying an electrical system, it's always best to consult with a qualified electrical engineer or licensed electrician. They have the knowledge and experience to ensure that the system is installed correctly and in compliance with all applicable codes and regulations. They can also provide guidance on selecting the appropriate components and materials for the specific application. In the context of this 208 volts 3-phase 200 amp system, let's consider some additional scenarios and design considerations. Suppose the building is a retail store with a variety of electrical loads, including lighting, refrigeration, HVAC, and point-of-sale systems. The engineer would need to calculate the total load demand to ensure that the 200 amp service is adequate. The NEC provides methods for calculating load demand based on the type of occupancy and the connected loads. The engineer would also need to consider the potential for future expansion. If the store plans to add more equipment or expand its operations, the electrical system should be designed to accommodate the increased load. This may involve increasing the size of the service conductors, the meter base, and the indoor panel. Another consideration is the location of the equipment. The disconnect and meter base should be located in a readily accessible location for maintenance and inspection. They should also be protected from physical damage and environmental conditions. Outdoor installations must be weatherproof and protected from corrosion. In some cases, it may be necessary to install surge protection devices to protect sensitive electronic equipment from voltage surges. Surge protection devices can be installed at the service entrance or at individual equipment locations. They help to divert excess voltage to ground, preventing damage to electronic components. Regular maintenance is essential to ensure the continued safe and reliable operation of the electrical system. This includes inspecting the disconnect, meter base, and indoor panel for any signs of damage or deterioration. Loose connections should be tightened, and any corroded components should be replaced. It's also important to periodically test the overcurrent protection devices to ensure that they are functioning properly. Circuit breakers and fuses can degrade over time and may not trip when they should. In addition to routine maintenance, it's important to have a qualified electrician inspect the electrical system periodically. They can identify potential problems and recommend corrective actions before they lead to more serious issues. A thorough inspection can help to prevent electrical fires, equipment failures, and other hazards. The installation of a 208 volts 3-phase 200 amps disco, meter base, and panel board has many national electrical code considerations to follow. Article 230.70 A1 of the NEC covers the location of the service disconnecting means. It states that the service disconnecting means shall be installed at a readily accessible location either outside of a building or structure or inside nearest the point of entrance of the service conductors. The disconnect is required to be readily accessible so that it can be quickly operated in case of an emergency. The disconnect must be located either outside the building or inside nearest the point where the service conductors enter the building. This ensures that the disconnect is easily accessible to emergency responders and maintenance personnel. NEC Article 230.71 limits the number of service disconnecting means. For one building or other structure served, the service disconnecting means shall consist of not more than 6 switches or 6 circuit breakers mounted in a single enclosure, in a group of separate enclosures, or on a switchboard. There are several reasons for this requirement. Firstly, it simplifies the process of disconnecting power to the building or structure. If there were more than 6 disconnecting means, it would be more difficult to quickly and reliably disconnect power in an emergency. Secondly, it reduces the risk of accidental energization. With fewer disconnecting means, there is less chance of someone accidentally energizing the wrong circuit. Thirdly, it simplifies the maintenance and testing of the electrical system. With fewer disconnecting means, it is easier to inspect and test the disconnecting means to ensure that they are functioning properly. NEC Article 250 covers grounding and bonding. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, which helps to trip over current protection devices and prevent electrical shock hazards. Bonding connects all of the metal parts of the electrical system together, which helps to equalize the voltage and reduce the risk of electrical shock. NEC Article 310 covers conductors for general wiring. The conductors must be sized appropriately for the load they will carry. The conductors must be protected from overcurrent. The conductors must be installed in a safe and workmanlike manner. The ampacity of the conductors must be selected from the tables in NEC Article 310. The ampacity is the maximum amount of current that a conductor can carry safely without overheating. The size of the overcurrent protection device must not exceed the ampacity of the conductor. The conductors must be protected from physical damage. The conductors must be supported properly. The conductors must be installed in accordance with all applicable codes and standards.